how would you feel if I told you that after this talk, after you leave this door, your car is going to burn half of the gasoline, or that you will have to pay half the price of the gasoline? Or that the next time that you go to a bar to grab a beer, you will just pay half the beer and not have to pay for all of it. My name is Pablo Ribalta. I am an engineer at Nvidia, and today I will be talking about mixed precision training. I will be explaining you what is the difference between training fast, training slow, and what does it take to get there.
Where do you live now?
Yeah? Well, I will stay nearby. So I assume that if you have stayed until so late, it's because you are interested, you know what this is all about, but I will try to start by explaining a little bit the whole thing. There is artificial intelligence, which is this grand project to build this, substitute of the human mind performed by a machine. It's like this very open goal. This is something that's more like an ideal. But inside there are different subfields. One of them is machine learning, which is machines that are trained to be smarter. We all here more or less have some experience with writing programs. We know how difficult it might be sometimes. You might forget something, you might introduce a bug, it will not perform in the way you want. And if you want to teach a machine to play, for example, chess, you need to write a lot of code, you need to write a very difficult program, and it's better just to have the machine learn it and develop its own strategy. So this is machine learning. We don't program machines to do something, we program machines to learn to do different things. Inside machine learning, we have deep learning, which is yet one level deeper. The difference between deep learning and machine learning is that we don't tell the machine what is interesting. We don't tell the machine what it has to pay attention to. The machine figures it out on its own. So it's not only about learning, it's also about picking information about what is interesting, what is relevant. So we can say that deep learning is this reincarnation of this artificial neural networks. It's not a new idea. This is something that has been around since the 1970s. But there has happened something in the last 15 years that has changed everything. This was the adoption of the GPU, which has been pioneered by Nvidia, which has brought an immense amount of computational power to the field, making training these networks possible. So as you see, there is not much difference in, the technology the idea, the theory behind that, but in the last years, the performance has gone up. The difference is that now we can go to bigger networks that are in layers, not only in neurons. We have new training math. We have scale. We can go not only from training in one computer, we can go into clusters that have hundreds of GPUs, and this has opened up the door to a lot of different problems. The key benefit of deep learning, as you see, is that it's very, very accurate. It's surprisingly accurate, sometimes even surpasses humans. It's unbelievable, but it's true. It learns the features from raw data, so it learns to pick up what is interesting, and it doesn't require you to fool around too much with the features. So the whole idea is based that practice makes perfect. Let's imagine that you are trying to learn how to shoot some arrows. In the beginning, you will be very bad. Your arrows will go all around because you have never picked up a bow before. But the hope is that with time, you will learn how to be more accurate. When you see that your arrows go all the time to the left, you will try to correct your shot and sort of like shoot to the right. If you see that your arrow goes down, you will start shooting a little bit lower. Eventually, you will get there, and when you will look at the center of the bullseye, you will be able to hit it. This is a perfect analogy of how these networks are trained. The process of training a network is iterative, it's repetitive. You give it examples, you try to predict the solution, and you see how far you got, and then you correct from there. There are two very important things in this beyond what is the network itself, the layers, the neurons, and everything. There are two things that make the difference. One is the loss function. What is the loss function? Have you ever played this game where they would close your eyes and you would have to try to find something and they would tell you hot or cold? So you would be getting hotter as you are approaching what you have to find. So the loss function behaves in a similar way. Loss function is an indicator of how bad you are, how much you suck. So you really want to bring this thing down. So in the same way, the loss function tells your network, okay, you're getting hotter and hotter and hotter until you just burn yourself 100% accuracy. So the goal is to reduce this loss. You just want to get this loss to the bottom. This is the difference between what you predict and what you get, or what it should have been. The second important part is the optimizer. We talk about an iterative process. Remembering about shooting an arrow. If you see that your arrow is going like 10 centimeters to the left, you have to adjust by a fraction of what you perceive is your error. The optimizer is what takes the loss and it says, okay, if I see that I am very, very, very bad, it means that I still have a lot of work to do. So I will try to correct much more than when I'm almost at the very top and I'm almost perfect. I want to correct just a little bit. So the optimizer is the one that makes the decision between, do I want to correct a lot or not? So these two guys work in parallel. They help each other. And they help ultimately to optimize your network and make your arrows go to the objective. Getting a little bit more formal. I don't scare everybody, but I thought, let's just get this thing out of the way and from a high level, training a neural network from a high level, in a more formal sense, networks are trained using backpropagation. What we see here are 3 neurons on the left, which are the inputs to our model. This big circle in the middle is where these inputs are combined, and this Y0 is the decision that we are outputting. So just imagine that you have 3 inputs that can be whatever, like you put a photo and you see it has pointy ears, it has mustache, and it has long teeth. And all these inputs are combined, and then your output is like, this is a giraffe. So it's not a giraffe, probably not. But from a mathematical point, this is what's going on. This thing is very cool, even if it doesn't seem so, because it's a universal approximator. What does that mean? This means that it can help you predict if this photo is a cat or a dog, or if this photo is a tumor or something else, or if this is a plane, or if it's something else. It's always the same thing. So you start to realize the potential that the systems have and how solid the theoretical background is behind it. This is achieved by assigning to each input and to each network, to each neuron in the network, some weight and some bias that tells you how important this feature is in the model. And when it's combined, it sort of performs like a votation. So you multiply it by the weight, you scale it according to its importance, and then you add this bias term that adds a little bit of nuance. So this is what we see in this circle in the middle. Is for every input, we take the value, multiply it by the weight, and add this bias term. What we have at the end, after I0 in purple, this I prime, this is what we should have predicted. This is what the network was what we were expected to get. And the difference between these two terms is what gives us the loss. The loss, which I remind you, is how far we are from the truth. Then this loss is utilized by the optimizer in order to fine-tune the weights, etc. So this thing happens not once, not 10 times. It happens millions of times during your training. It happens at an incredible scale because this network is very small, but neural networks or deep neural networks like we have seen have millions of parameters. So there are millions of updates being performed every second. It's staggering. So the way this update works, and I have to explain to you so you will understand what is the magic between mixed precision, is performed in two passes. The forward pass, when we produce the output. So it takes an input vector, we take some features, like for example an image, we compute the output based on the weights, and we generate the loss. It's fine. Then we perform the backward pass. We utilize this loss, we take the optimizer, and then we update our model. And this thing goes over and over and over many, many times. When we talk about real networks, we are not talking about 2 or 3 neurons. This example is very small, but we are talking about millions of neurons, especially when you talk about deep learning, where you have convolutional neural networks, who have hundreds of thousands, I don't know, can have tens of millions of parameters. So this thing happens at a scale almost unimaginable. At Nvidia, we realized that we have a very important role to play because we have this little thing called GPU, which is a supercomputer that is embedded in your system. This supercomputer is very good at performing operations in parallel. So if you model this network, each layer as a matrix, then you can multiply it very fast. So every time that you try to calculate a value inside the network, if you do it by matrix multiplication, you can do in one step, you can calculate the values for the subsequent layer. So what we have seen before, where you have a matrix that you have to evaluate each position itself, just imagine that you can do it all at once in one step. So you are basically printing new matrices all the time. So what you do is you take the inputs, multiply them by the weights, and add the biases, and you do it all at once. So instead of having to perform 9 different operations, you can do it all in one step. This is important because it will lead us to understand something. In the last years, Nvidia has developed a revolutionary technology for deep learning training. This technology is called Tensor Core. Has anyone heard about Tensor Core before? Okay, very good. So Tensor Core is an improvement that allows to do in one step a multiplication and addition at once. If we think about what we've seen before, where in order to evaluate a network, a layer in the network, we have to perform a multiplication by the weights and the biases, we might think, oh man, that is great, because we don't have to do 9 operations. We just do this operation, we just do this multiplication, addition, and we get the result. So with Nvidia Tensor Core, we can do it even faster because it only takes one step. These operations are fused. This means that from the previous generation, which was Pascal, to the last but one, which is Volta, we can get an exponential improvement in our performance. We can get up to 12 times more throughput. And you say, wow, but we are only fusing 2 operations. How this can happen? Well, it happens because the multiplication is not performed in the same way as it used to be done. Normally, values inside the network are very nuanced. We want to keep floating point numbers because there might be small differences that might help us distinguish between, I don't know, an elephant and a whale or whatever we want to distinguish. It might require just a 0.0, a fraction of a unit to tell you that this is something or it's something else. So for these, we use floating points of 32 bits. But if we only use 16-bit representation, then something very funny happens. It means that before we needed 32 bits to store a number, but now we only need 16. So in the place where we could fit 1 number, now we can fit 2 numbers. If we take it for the 2 operands, so these are the place where we could fit 2 numbers, now we can fit 4 numbers. And we can multiply them all at once, and we can perform an addition on top of that. This is where the 12 times throughput comes from. And if we are only able to harness this performance improvement, this thing is huge. This thing, I'm talking to you about a boost of 3 or 4 times faster training than what you already have. And you might say, okay, yeah, that's pretty cool, but I really don't want to, you know, but what does it take to do that? You know, I just don't want to have to write my model and then mixed precision model. It doesn't require any change in the architecture. Just realize about that. You have to do absolutely nothing. And I will try to explain you how it works under the hood, and then I will try to explain you how to start taking advantage of it. But before, I want to tell you that it's not all that beautiful. There has been a lot of hard work. There has been a lot of hard work to be done by NVIDIA engineers to help you to do this. Because when you take a floating point number of 32-bit and you compress it to 16-bit, of course, you are losing some range of representation. Some numbers are simply not representable in FP16, and they are representable in FP32. So this might be very problematic when you have to update your weights. You know, we have our network, we want the network to improve, and we want to tweak it just a little bit so it will go to the desired objective. But this little bit might not be that representable. We might have problems, for example, with gradient underflow. We might have to calculate the gradient to see in what direction do we want to update, but the gradient is just so small that it becomes 0. If the gradient becomes 0, what's going to happen? We are not learning because we don't get any feedback, so that's pretty bad. We also want to maintain the precision of the network. If our network has 75%, 95%, 99% accuracy, we don't want to get worse. So how can we ensure that? So, well, this is, I mean, yeah, commenting on the figure. These are the activations that you get when you train in a ResNet 50 on Caffe. Never mind. As we see here, you cannot see very well the numbers, but on the left is 0. What we see is that the gradients that we obtain are very, very close to 0. So we are at a very high risk of losing all these gradients. If we make this figure in a logarithmic scale, and we try to see what of these gradients are representable in FP16 and FP32, we start realizing that the majority of these gradients are just simply not representable in FP16. So there's something to do about that. You know, we see that the representable range is on the second half, and we see that we are just losing a lot of updates. If we don't do anything about that, we are just simply not going to learn. So there are several things that we attack. The first one is the imprecise weight updates. What can you do if you lose precision in your weight updates? So you want to keep the master weights in FP32. You want to keep them in FP32 because you want to keep every last bit of nuance in your weights. You want to be able to very finely grained detect differences in things. You don't want to lose precision there, because that would be catastrophic for your learning. For the gradient underflow, the gradient is the direction that we have to adopt in order to learn. When you fire an arrow, if you are going to the left, the gradient will tell you shoot a little bit to the right. So if you are not able to represent this gradient, you will clip it, it will become 0, and the network will tell you, oh, you are shooting fine. You just shot very far away. It's fine. What you want is to make this gradient as big as possible. You might say, why? Why would I like to make this gradient as big as possible? Because the gradient is correlated with the loss. So if you increase the gradient, then you can decrease the loss. And if you operate in the loss at 32-bit, so then there's nothing lost. So this is a way to compensate for the gradient. This is a very lightweight operation. So you just simply scale the gradient and then take the loss that is proportionally small. So under the hood, what does your framework of choice, TensorFlow, PyTorch, whatever, do? This is the loop that your training goes through all the time, every time that you train. It starts at the input. You take the input, you take a new image, whatever you want to classify, and you perform the forward pass, and you obtain the loss. See, now this thing will be helpful, but I will just point it here. Yeah, so I don't want to discriminate the other side. So from the forward pass, we go to the loss. And the loss, we have to use it for updating our model, so it goes to the backward pass. In the backward pass, what we do is we go through all the weights and we update them. Later, these weights are utilized in the next forward pass, and the cycle repeats and repeats all over again. So how do we introduce mixed precision here? How do we do all these things that we wanted to do? How do we operate with FP16, and how we make sure that we don't lose our updates? It takes several steps. The first one is that we take our input and we cast it to FP16 if it's not in FP16 already. So if we have an image that is float 32, we can cast it to FP16. And TensorFlow or PyTorch, the library that is underneath, which is called cuDNN, will choose the appropriate kernels to spin and will operate using Tensor Cores automatically. You don't have to do anything. After this, your entire model is operating in FP16. You are in low precision, but this is not mixed precision yet. Mixed precision means that parts of it is done in FP16, parts of it is done in FP32. So we've talked about the loss. Here we will get the loss in 16-bit, the backward pass will fail, we will be unhappy, our model will not train. We don't want that. So what we have to do is to cast the loss to FP32. Like that. It's not a problem if the loss was 0.33333 and we lose some decimals. It's not a problem. This is the same as if you are on a plane flying and you are in autopilot, and instead of being at 10,000 feet, you are at 10,002 feet. Does this make a difference? It doesn't, because it will self-correct. Once we take this loss, we pass it to FP16. Sorry. Once we take this loss, we convert it to FP16. It will happen anyway. And we use it to obtain the weight gradients. Okay. So when we update our weights, these weights then are casted to FP16 and sent back to the forward pass. So what is going on here? We are taking the loss. We are taking the loss in FP32, and we convert it to FP16, and we use it for the backward pass. And why is that? This is because in the backward pass, we need to update all the weights. And this is also done via matrix multiplication. We want these matrix multiplications to be done by Tensor Core as well. So essentially, we are trying to keep our forward pass and our backward pass running on Tensor Core all the time. After all, what we want is to update our weights, which are in FP32, and then use these weights in the forward pass. So this thing keeps spinning all the time. Ultimately, as we have said before, if we want the updates to our weights to be precise, we need to cast them to FP32. Okay, so this is awfully complicated. You might say, why should I go through all this thing to implement mixed precision? I'll tell you, I will remind you, you don't have to do anything because we have done this for you. Oh, forgot about the loss scaling. So if we want, as I said before, if we want our update to be meaningful, what we can do is to scale the loss, recover these decimals that we lose when we cast it to FP16, and then divide it when we update the weights. This way, we increase our loss, but the update is proportionally small. So, all in all, the changes that we have to do keep the forward and the backward pass running on Tensor Core. This is the part that we want all the time to be optimized, because this is where 95% of the time is spent. Casting, scaling, this is a very lightweight operation. This almost doesn't take any time. And it's done with several objectives. What you want is not to have nuns during training, because if you get a nun in your model instantly will crash. None means not a number, so it's a number that is not representable, number is corrupted. You don't want to have that. And what you want is to have a stable gradient. What you want is to not to have a very bumpy gradient that will just get you stuck. So if you want to use mixed precision, this is what you have to do. Who from here uses TensorFlow? Okay, who uses PyTorch? Okay. So for TensorFlow, you only need to set up an environment variable, which is TF enable auto mixed precision 1. If you have this, TensorFlow will pick it and will say, oh, this guy knows about Tensor Cores and wants to use Tensor Cores. Nothing else to be done. If you're using PyTorch, you have to import a module called Apex, Python Apex, and simply wrap your initializer and your optimizer on that, and it will just work. You don't need to change anything. Everything that happens underneath in the framework, it will be, taken care of itself. However, this will not happen with the PyTorch or with the TensorFlow that you download from Google or from wherever. This functionality is available in the Nvidia containers. Nvidia containers are ready to run deep learning software. So have you used Docker, any of you? Okay, so Nvidia provides you with Nvidia Docker. The problem with Docker, if you have a GPU, is that you can run a container, but you cannot touch the GPU because a container is just simply a virtual machine. So what Nvidia Docker gives you is that you can run a Docker container, but to utilize fully the GPU. Why? Because CUDA, cuDNN, everything comes installed already inside. You have containers for TensorFlow, you have containers for PyTorch, for whatever you want. You can use it anywhere, and it's for free. You don't have to pay for anything. It is for everybody. It contains the most optimized versions of every framework that we specially compile to have all these advanced little goodies. It has examples of the most popular models. Do you want to use ResNet? Do you want to use SSD? You want to use whatever? So it's there, it's implemented. You can use it to inspire yourself to write your own models. Ready to use. It comes with scripts that will get you started. The way it works, as I said, is platform independent. It doesn't matter if you use Linux, if you use Windows, if you use Mac. Yeah, I think we support Mac. So as long as you have Docker, it will work. If you want to try it, here is a link, github.com, Nvidia Docker is open source, so you can see exactly what is in it. We are not putting anything there that you don't want. And if you are interested, you can take a look at what's coming, which is different support for different formats, for training in different formats, not only on FP16, but also in, what do I have here? int8 or int4 in the new architecture, which is Turing. So if you are considering buying a GPU, buy a Turing GPU, because this is what happens when you use a Turing GPU and you do mixed precision in yet lower precisions. You go from Pascal, which is super slow, which is super bad, super old, don't get Pascal, to 32 times speed up. It can be done. I've seen it working. It's amazing. So there are a lot of exciting things there to come. They used to tell you that bigger is better. Get a bigger GPU, it will work faster, everything. But there is much more than just better hardware that you can do to train your models faster. So if this sounds interesting to you, this is the slide that was shown in the beginning. If you want to get started with machine learning, just check our containers. I'm sure that everyone here has gone through the pain of installing CUDA, installing cuDNN, installing TensorFlow on top, and then you realize that your TensorFlow version doesn't match cuDNN version, and you have to uninstall TensorFlow and cuDNN. And then you install a new cuDNN, but you forgot to install CUDA. Yeah, forget about that. Just download the container that has the version of TensorFlow that you want, and that's it. Are you a researcher? We sponsor researchers. We offer them GPUs, we offer them collaboration. We offer them know-how. If you have a problem that might require a Tensor Core or that can benefit from Tensor Cores, let me know. My email is at the bottom of the slide. Shoot me an email, we'll talk about it. We'll see what we can do. We recently granted 35 Volta GPUs to the University of Warsaw. So yeah, don't be a fool, just get the GPU. Do you want to be part of our mission? Do you want to work on hard problems? Do you want to make changes that improve the life of millions of developers? Let me know. Send me a CV, contact me on LinkedIn, send me a message, whatever you want. Send me a pigeon to my house if you want with a letter. It doesn't matter. Just let me know if you are interested and we can see. I will be sharing the slides after the presentation. So here there are some links so you can learn a little bit more about mixed precision training. All this it's very well explained. There are perf accuracy numbers in the paper that was presented to ICLR last year, called Mixed Precision Training. Here there are some articles as well in the Nvidia blog about mixed precision training, some performance guide for deep learning, some talks in GTC as well, and a link to PyTorch Apex repository, but is in GitHub, so you can Google Python Apex and you will have it. So yeah, time for questions. Thank you very much.